Thank you, and thank you for inviting me to speak here. It's just so great to have another opportunity to be in Lumini. So first of all, as you might notice, I'm giving a slides talk. And there's a problem, which is that slides talks are just impossible to follow because the information disappears too quickly. So everyone, take out your laptop. You're all young, hip people. You have laptops with you. Just take it out. Go to this website. You'll have the slides available for you. And that way, you won't need to take notes or worry about information disappearing. And you can go back as you need to. And if you get bored, you can read Facebook or whatever. Like it's just completely like. So it's highly advised by the speaker to do this. Yeah, so, well, OK. So the thing I want to do, OK, the reason I'm using a slides talk is that I want to give a kind of, well, more elementary talk, maybe. So apologies for things that are redundant, but let me just emphasize, well, I want to say a few of the features I want to emphasize in this talk about geometric Langlands. So geometric Langlands would, like at a very coarse level, what it is that it predicts that you can compute some cohomology groups involving some moduli spaces of G bundles for georeductive group, G bundles on things like curves, in terms of the Langlands dual group. And so this theory, it has many remarkable features. But let me just point out two aspects that, well, that for me stand out. So one is that Langlands duality, it's something kind of weird for reductive groups. It's really a combinatorial thing, and like you can't. It's not like an algebra geometric construction where you can just easily say like it's this. So like geometric Langlands, it's problems in algebraic geometry about this duality of reductive groups, which is of kind of different nature. And one of the problems is just like, how do you connect these two things? It's one of the first things that stands out when you learn this set of ideas. And the other thing is that there's some huge infinite dimensional things that you run into like early on in the theory. Just you can't avoid things like the loop group or whatever. And these things, they're almost formal to the point that it's hard to do like fine combinatorics with them, the way that this definition of Langlands duality just completely requires you to do. So it means that, well, maybe you look at this set of conjectures and you say, like, how could you ever possibly prove these? Because these things are of such different nature. Like, I don't even know where to start. You need some number of ideas. And so what I would like to do in this talk is to give, in just one example, a kind of feeling for, like, how you can connect the group and the Langlands dual group, and how you can ultimately exploit these ideas to treat problems that at first seem completely intractable. So I'm going to have to like make choices in order to do this about, well, some things that I think are important and some things that I just like that are getting lost, that are expenses of this. So one expense is that I'm giving a slides talk, and other things are that, well, I'm going to focus on the kind of elementary geometric aspects of this, and not maybe so much on some of the finer details, chasing cohomological shifts and things like this. And also, I'm going to sweep under the rug many formal aspects, some of which are kind of pleasant. And the last thing is that since I'm focusing on the elementary geometric aspects as much as I possibly can, this is going to be probably boring to a lot of experts. I'm going to talk about things that people in this room defined, looking at you. And yeah, so sorry. Yeah, so the problems I want to talk about fit into exactly this sort of pattern. So well, the only way that you could possibly prove something about these infinite dimensional moduli problems is to reduce them to finite dimensional calculations, which is where you have some, well, there's like this nice theory of perverse sheaves that lets you actually compute stuff miraculously. And so what I'm going to do is focus on the finite dimensional aspects of the story, first of all. And what we're going to compute are what are called twisted cohomology of Zastava spaces, where I will remind you what both of those phrases mean in some detail. And then at the end, I want to talk about an application of these computations to what's called the semi-infinite flag variety, or the principal series category, or whatever. OK. So first, I'm going to start with this twisted de Rham cohomology. So this is an invariant that we're going to compute for certain varieties. OK, so if S is a smooth variety over a ground field K, which is of characteristic 0 always in the story, and F is a function, it's just like a regular polynomial function, then the twisted de Rham cohomology, it's some kind of invariant, and it measures something about the singularities of the map F, which we'll see in some examples. So first of all, this twisted de Rham complex, it looks like the usual de Rham complex. So you take functions mapping to one forms, going down to top forms, and you have de Rham differentials. And then you have a correction term according to this function f. So you add this correction term of wedging with df to the de Rham differential. And it's easy to see this actually defines a complex. And then you can define twisted de Rham cohomology as the hypercohomology of this complex. So it's something very explicit. So here's the most basic example. So suppose that S is equal to A1, and F is the identity map. So in this case, the twisted de Rham cohomology, it's computed by this very explicit complex. And in fact, this complex, it's completely acyclic, and twisted de Rham cohomology therefore vanishes. So just as a first thing to get a feeling for it, there are no non-zero zero cocycles. Sorry, it's a bad phrase, but so if you had a zero cocycle, that would be a regular function on A1, so a polynomial function, with the property that its derivative is equal to minus itself. And that, that means that this function has to, complex analytically, that means that this function has to be a scalar multiple of e to the minus t, as I'm teaching in my differential equations class this semester. And well, you can't have that for a polynomial function. But that does show the following feature of this theory, which is that if you work complex analytically, then these groups, they coincide completely with the usual de Rham cohomology groups. So maybe no surprise that it vanishes in first degree, because it's in some way, because you're used to first cohomology of A1 vanishing, but you're not so used to the zeroth cohomology of A1 vanishing. OK, as a second example, suppose now that S is A1 minus 0, mapping into A1 as the embedding. So in this case, the twisted de Rham cohomology, it's something very explicit again. So the zeroth cohomology is going to vanish, and the first cohomology is one-dimensional. And you don't need to remember this formula, but here's the formula to give the isomorphism. You map omega 1, and I claim that the kernel of this map is exactly the image of this de Rham differential. So that's something like you take your one form, you multiply by e to the t, and you take the residue, which doesn't really make sense because it's algebraic, but you can make sense of it by that formula. OK, and finally, these two examples show the following feature. So if f is both smooth and proper, then it's not hard to see that the twisted de Rham cohomology actually just completely vanishes. So that's one thing I mean that it measures the singularities of the map f, is it's a kind of obstruction to f being smooth and proper. So now I want to give a version of this twisted de Rham cohomology with coefficients. And in order to do that, I want to just rewrite the definition in terms of D-modules. So remember from my talk on Monday that D-modules are complexes of quasi-coherent sheaves with a flat connection. And I'm going to denote the corresponding DG category by D of S throughout. So also remember that this category D of S, it's defined for singular schemes also. So you can't use the same quasi-coherent sheaves with flat connection, but you can take quasi-co or int-co of the de Rham pre-stack associated to your finite type scheme S, and you get a very nicely behaved theory, as was explained on Monday. And just a reminder that if you have a map from S to T, then you have these two functors, f upper shriek and f lower star de Rham, and all I'll really need is the existence of these functors for the purposes of this talk. Well, in some sense, for how to compute them in nice situations. So now let C be the exponential D module on A1. So by definition, this is going to be a certain line bundle with connection. So it's the trivial line bundle on A1. And the connection is given by this formula. Nabla of f is equal to df plus f dt. So then if you have your scheme S with your map f to A1, you can redefine this twisted de Rham cohomology as pull back this exponential sheaf and then push it forward to a point. So these push forwards for smooth varieties are computed by the corresponding, de Rham cohomology complex with coefficients. And if you just track what that means, it gives exactly this. And then maybe there's some cohomological shift that doesn't matter for these purposes. OK, so now this allows us to define twisted de Rham cohomology with coefficients in any D module F. So what you can do is if you have your D module F on S, you can pull back your exponential sheaf according to the map F, tensor with F, and then push forward to a point. So one example where you might care about this is that if S is singular, there's something called the intersection cohomology D module on S. So if you know perverse sheaves in D module as well, this is, well, it's the first thing you learn probably. But in general, the way this intersection cohomology works is that for S being smooth, this is just the trivial line bundle with the trivial connection. So no correction. It's just the de Rham differential or the exterior derivative. But in general, it's something complicated that measures in a sort of complicated way the singularities of S. And then the miracle is that there's this theory of perverse sheaves that, although it's something complicated, you can still prove very remarkable theorems about this in a lot of situations. So one thing that would be of particular interest is, since this sort of plays the role of the constant sheaf for a smooth variety, you might think that twisted de Rham cohomology with coefficients in the intersection cohomology, that this is maybe the right analog. Or at least I would encourage you to think that this is the right analog for a singular scheme S. OK, so just what did you need to remember from all of that? So first of all, there is this notion of twisted de Rham cohomology, and it measures something about the singularities of a sheaf relative to a given map, relative to a given regular function. And as Dario is going to explain in the next talk, in some form, this twisted de Rham cohomology plays the role of exponential sums in number theory. So it has a kind of central role in geometric representation theory. If it's regular holonomic, then it's like the global cohomology of the vanishing cycles is computed as the cohomology of this twisted de Rham complex. At least if the map is proper or something like that. OK, so Zastava spaces. So these spaces were introduced by Finkelberg-Mirkovich, both in real life, in history, and in this week. So each of Finkelberg and Mirkovich defined Zastava spaces this week, and I will give a third take on them. So, well, the representation theory of many interesting objects can be found in these Zastava spaces, which I think is probably what got people excited about them in the first place. And the role that they're going to play for us today is that they have, whatever they are, they have a kind of inductive nature in the sense of proof by induction. And that makes them a very useful computational tool for some problems in geometric representation theory. So I'll explain what these spaces are, explain in some period of time. It'll take a little bit what the inductive nature of them is. And then we'll see an example where this inductive nature is very helpful in doing computations. OK, so there are many references. So there's the original paper by Finkelberg and Mirkovich. There's a follow-up paper that added Kuznetsov and Fagan. And then there's a paper by Braverman, Finkelberg, Gatesgory, and Mirkovich that pushed those ideas further. There's a Braverman-Gatesgory paper, which is relevant to what I'm going to be talking about today. So I just want to flag it, because I'm going to appeal to results from it. There's the paper I'm talking about right now, which is available on my webpage. And finally, Ivan has some nice notes on his webpage that give an introduction to Zastava spaces, and that are meant for a beginner to learn some of these things. OK, so in order to talk about these, I just need some quick notation from reductive groups. So let G be a reductive group, so like GLN. And it's going to have Borel B, unipotent radical N. I'm going to choose an opposite Borel also. And then T will be the intersection, which is the maximal torus. So what you should think is we have square matrices, upper triangular matrices, strictly upper triangular matrices, lower triangular matrices, and then the torus is diagonal matrices. So in this theory of reductive groups, I can associate the lattice of weights of characters of the torus, the lattice of co-weights, which is dual to the lattice of weights, and can be thought of as maps from GM into the torus. And inside of here, I pick out the roots. So these are certain weights, and these are the weights of T that occur as eigenspaces for its action on the Lie algebra of N. And then an important feature of this theory of reductive groups are that the roots are in bijection with so-called co-roots. So for every alpha, there's an associated alpha check with the basic property that alpha check paired with alpha is 2. And now I'm going to need lambda check pos to be the span of the positive co-roots. So just to remind you, this is freely spanned over the non-negative integers by some simple co-roots. So that's what alpha check I means, simple. OK, so just very quick review of how this stuff works. So for GL2, your torus is 2-dimensional, so your lattice is Z2. Your co-weights are also Z2. And then this is what alpha and alpha check are. Note that their dot product is 2. So that's what it means that the pairing of alpha and alpha check was 2. And for SL2, the situation's somewhat similar, but a little bit more degenerate. You quotient by a hyperplane. You quotient by a line for the weights. You take a sub-hyperplane as the co-weights, and alpha check are the same. And for PGL2, it's basically the same, except now the weights are sub, and the co-weights are a quotient. And so what you should notice is that for GL2, the picture is symmetric. For SL2 and PGL2, you swap the role of the roots and co-roots and the weights and co-weights. And that's what Langlands duality for reductive groups is. Like that is how it's characterized. So these reductive groups, certainly they're classified by their root data, and dual root data correspond to dual reductive groups. But this duality, it's something really strange, because what we mean when we say SL2 and PGL2 are dual is this slightly esoteric thing. And then we're supposed to prove things about it. And yeah. So, OK. The basic approach to connecting the group and the dual group through geometry is through some kinds of, various kinds of infinite dimensional geometry. So the affine Grassmannian is the starting point for this. So I'm going to let big K be the field of Laurent series, big O be the subring of Taylor series. And then in this case, I let the disk and the puncture disk be the spectra of these rings. And now G of O will denote the group scheme of infinite type, which parameterizes functions on the disk. G of K is the in scheme of infinite type of functions on the puncture disk, valued in the group, valued in matrices, if you like. And then the simple examples are that when G is equal to GA, then G of O is just this infinite dimensional affine space. And this Laurent series is a union of such things under kind of inclusions. You think lower and lower terms in the Laurent series expansion. And just note, those weren't formal definitions, so they shouldn't be appealed to as such in a paper, but this isn't a paper. So, OK, so the affine Grassmannian is now the quotient G of K mod G of O, and you should think of it as parameterizing G bundles on the disk with a trivialization on the puncture disk. So it's a kind of flag variety for this loop group G of K. So some examples of this affine Grassmannian. So for GA, this thing is a union of affine spaces. That's a feature which always holds true for unipotent groups, just by easy reduction to the GA case. For GM, at the reduced level, it's just the integers, and that's all we're going to need today. More generally, you extract the co-weights from the affine Grassmannian for T, so it's a kind of duality already. So the isomorphism sends lambda check to lambda check of T, where T is the uniformizer in our Laurent series ring. And finally, the affine Grassmannian for B, it has connected components which are the same as the points of Ger T, but and each of these components is an ind affine space. So this is a generalization of the statement for n. OK, so the following general features always hold. It's an ind scheme of infinite type, unlike that loop group, which was infinite type. And if G is reductive, this thing is ind proper. So for example, in the case when we have a torus, it's just a bunch of points, more or less. And yeah, so now if you want to understand this affine Grassmannian for a general reductive group beyond the fact that it's improper, the first thing you do is you consider the n of k orbits. So these are indexed exactly by the co-weights. And in fact, what's really going on is the map from the affine Grassmannian for B to the affine Grassmannian for G is an isomorphism on k points. But it realizes the affine Grassmannian now is a union of these infinite dimensional affine spaces. So they're very different at a scheme-theoretic level. So each one of these orbits, parameterized by the co-weights, it's an ind affine space. It's locally closed. And here are the closure relations between the orbits. So this ger b mu check is going to live inside the boundary, maybe, of ger b lambda check whenever their difference is positive. So that one thing you see from that is, since this lambda check pos is infinite, is that these orbits, well, they're certainly infinite dimensional, and they're just completely infinite codimensional also. And for this reason, among many others, they're sometimes called semi-infinite orbits. So that's where this phrase later will come from for semi-infinite flag variety. So you should think about these as Schubert cells inside of the flag variety. So those are affine spaces inside of G mod B. So if this is some generalization, then these are ind affine spaces inside of this thing. So on to Zastava spaces. So this is the third time they're being defined, but just allow me to do it. So I'm going to define this Z lambda check 0 as the intersection of this one infinite dimensional orbit with the so-called, well, it's kind of transverse orbit for the opposite group. So it's an intersection of two infinite dimensional orbits, two infinite dimensional affine spaces embedded inside of this affine analog of, well, inside of this affine Grassmannian. So the space, it has some kind of partial compactification where I take the closure of ger b instead. So as one example, if lambda check is equal to 0, then this intersection, it's just a single point. Easy exercise. So Finkelberg and Mirkovich started the study of these spaces, and they showed that they're non-empty only for lambda check being positive. And moreover, somewhat miraculously, they're finite dimensional varieties. So they're intersections of infinite dimensional things inside of something else infinite dimensional, but you actually get a finite dimensional variety. Moreover, they're equidimensional, and the dimension is just rho paired with lambda check. So certainly in the case lambda check equals 0, that's compatible with the above. And finally, these are both affine varieties. So this ger n minus, it has a canonical map to GA, which is induced by the following procedure. So if I had the case of GL2, well, Dario will talk about this a lot in the next talk, but if I had GL2, then my n minus of k is just equal to GA of k, which is just, you think, k, and then you have a residue map down to GA. So sum of ai t to the I certainly maps to a minus 1. And in general, for a reductive group G, I should project to the abelianization and then sum over all coordinates. So the abelianization is a product of copies of k indexed by these simple co-roots. So from this, since the Zastava space, by definition, remember, I only compactified on the ger b side. So this, by definition, embeds into ger n minus, and I obtain an induced map to GA. So first, as an example, to get a feeling for these Zastava spaces, so I told you what it was when lambda check was 0. The next simplest case is when lambda check is a simple co-root. And then this map, it's going to actually, so for simple co-roots, this gives an isomorphism between the Zastava space and GA. And then this open part, it's GA minus 0 inside of that space. So this is the, well, the simplest case to understand in order to understand these Zastava spaces. So now a problem is to compute the twisted cohomologies relative to this induced map. So I'm going to give a first pass at a theorem that describes what these twisted cohomologies look like. So note that this problem, it generalizes our earlier things by this example. It generalizes our earlier computations. So first, if you take the twisted cohomology of the Zastava space with coefficients in its intersection cohomology, the thing just completely vanishes. Unless lambda check was equal to 0, in which case Zastava is a point, and you can't really make interesting, well, you can't make the cohomology of a point with coefficients in something non-trivial vanish. And for this open Zastava space, it's a slightly more subtle answer. So the ith cohomology is going to be the lambda check graded piece of the ith exterior power of the dual Lie algebra, like the unipotent radical of the Borel inside of the dual Lie algebra. So for example, if lambda check is a simple co-root, then the first statement generalizes the vanishing of the exponential cohomology of A1. And the second example generalizes our case of A1 minus 0, because on the one hand, well, we're computing twisted cohomology of A1 minus 0. On the other hand, we're computing the alpha I check graded piece of this exterior algebra, which is concentrated in degree 1 and one-dimensional. OK, so that preliminary version of the theorem, it's a simplification of a more sophisticated result using a more sophisticated version of Zastava spaces, which, again, well, this is what was really introduced by Finkelberg and Mirkovich. And this is where we'll see the inductive nature. So x is going to be a smooth proper curve going forward. And bun G, for example, is going to note the moduli space of G bundles on this curve. So now, to find this open Zastava space inside of this quotient, bun B crossover bun G with bun n minus, so it's a G bundle on the curve with a reduction to the Borel and a reduction to the unipotent radical of the opposite Borel. And what I require is that these two reductions be transverse at the generic point. So, well, if you trivialize your G bundle, OK. Should correspond to the open point in G mod B mod n minus at the generic point. This is the same as a map to G mod B mod n minus, and it should be the trivial, like the open point at the generic point. And lambda check just encodes the degree of the corresponding B bundle. So if you pass to sort of associated graded, the corresponding T bundle, that's the degree I want. OK, so Finkelberg and Mirkovich showed that the Z0 lambda check, it's actually smooth, and its dimension is twice the number we saw before. And moreover, just because of this Bruhat decomposition thing, because it's like a point and not a stack at the generic point, the Zastava space is actually a scheme, which is a nice feature. OK, so now just some quick notation, standard notation. So sim n of x is going to be my notation for the space of effective divisors on x of degree n. It's called like the symmetric power of x, or like everyone has seen this before. So for A1, you should be getting out AN. And more generally, well, this is slightly confusing, which is why I'm dwelling on it. So I'm going to let div lambda check effective denote the space of so-called effective lambda check positive value divisors on the curve of total degree lambda check. So you should think, like in the way you think points of sim n x are like points of x with positive, well, non-negative integers attached to them. These are the same. It's just that now I take values in this positive co-weight space. And so when you write lambda check as a sum of these simple co-roots, then the space of effective divisors is just a product of the corresponding things. So it's completely trivial. OK, so there's a canonical map from this open Zastava space to the space of divisors that measures the failure of this transversality. So remember, you're generically transverse, but you could fail to be transverse at finitely many points. So one thing that this means is that for lambda check equals, so this will attach a divisor to a point in Zastava space that measures the failure of transversality. So the support of the divisor and how heavy it is telling you something about this failure. And so one thing that means is for lambda check being 0, you just recover a point, like in the case for the affine Grassmannian. And here's how you get the divisor. So you just take the associated graded, the like T bundle associated with your B bundle. Everything is trivialized at the generic point of the curve, and therefore you get a divisor, a lambda check value divisor, and it's effective of this degree, claim I. What? OK, so one example in the case of GL2. So here, lambda check corresponds to, just to get a feeling for what this thing actually is. So lambda check now, it's just an integer. And what this Zastava space parameterizes up to those same twists that I'm ignoring is the following. So it's going to be a rank 2 bundle with 2 extensions. One of them just an extension of O of x by O of x, and the other one an extension of O of d by O of minus d for some divisor. So that's like the associated divisor for this thing. And what I require is that the two things be compatible in the sense that like those diagonal maps should be the standard embeddings. So one thing that you should note from this picture is that away from the support of D, my extension is just completely split. So that's the sense in which everything is trivialized away from the support of the divisor. So first of all, so I have this map from this open Zastava space down to the space of divisors. And if you think out what the definitions are, the fact, remember, affine Grassmannians parameterize G bundles trivialized away from a point. In these Zastava spaces, everything's trivialized away from some finite set of points. So if the divisor is concentrated at a single point and you chase the definitions, what you'll see is that you're just recovering this earlier notion of Zastava space. So one thing is that it's a bit remarkable that this open Zastava space is smooth because these intersections in the affine Grassmannian have no reason to be. And I just also want to note that the numerics are very friendly here. So the dimension of the total space is the dimension of the base plus the dimension of the fiber. It's kind of plausibility that those numbers make sense, at least. So more generally, if you wanted to take the fiber at some divisor that was maybe concentrated at several points, you just take the product of the corresponding Zastava spaces. So this means that Zastava factorizes. That's the word for it. It's kind of, well, one of the remarkable features about this is exactly what I mean by the inductive nature of these Zastava spaces. So note that when I'm on the space like corresponding to lambda check, then as long as my divisor isn't concentrated at a single point, the fiber, it's described in terms of Zastava spaces for lower lambda checks, right? Everything occurring there, lambda check I, has got to be smaller than lambda check unless the divisor is concentrated at a single point. So that tells you that what you need to understand to make a kind of inductive argument is basically what happens when points collide. OK, so now a global version of our problem. So up to these twists that, again, I'm ignoring, there's some canonical map from this space, from the stack bun n minus to GA. And now that gives a map from this open Zastava space to GA, and it recovers our earlier maps at the level of fibers. So for example, this now gives a description of these open Zastava spaces. So for lambda check a simple co-root, it's just x times GA minus 0 again. And then for GL2, there's just a comment about this twist. We don't really want extensions of O by O. Remember that that occurred in our earlier picture. But what you really want is an extension of O by omega 1 so that you get a class in H1 omega 1, which is a number. So that's the map to GA from bun n minus in this case. But you can just completely forget these twists. It doesn't really matter. OK, finally, I'm going to state that there's a version of this Zastava space that's like the closed, this partial compactification of Zastava space from before. So it has a map to GA, and it has a second map to the space of divisors, and the fibers are the spaces we saw before. It's just completely everything you expect. The only thing is that they're slightly more technical to define. We took the closure in the affine Grassmannian before in order to define the fibers. So like, you don't need to know the definition. Ivan gave the definition yesterday in terms of the affine closures, but you just take on faith that they exist. So here's now a version of this result, which is now for these big Zastava spaces. So it's a kind of parametrized version. So if you take the intersection cohomology sheaf of the Zastava space twisted by the character psi, so remember we have a map to GA from this closed Zastava space. And now I push forward to the space of divisors. So it's a kind of relative over the space of divisors version of this twisted de Rham cohomology. Then this complex just completely vanishes unless lambda check is equal to 0. OK, so now here's the version for open Zastava space. So now suppose I take the intersection cohomology sheaf for this open Zastava space twisted by this character. So first of all, this open Zastava space is smooth. So up to a shift, this is just the constant sheaf twisted by the intersection by the character psi, and now pushed forward to the space of divisors. And what will happen is that this is concentrated in cohomological degree 0 on the space of divisors. So it's a perverse sheaf, so to speak, and which is a quite remarkable feature. Moreover, there's an explicit description of what this sheaf is. So it's a little complicated, but here's what it is. So you take this n-check, the same n-check that appeared before. So the Lie algebra of the Langlands dual unipotent radical of the Borel. And it's something, so this C dot of n-check that's appearing everywhere is the homological Chevalley complex. So this is like the complex that computes Lie algebra homology with coefficients in the trivial representation of n-check. So it's some very explicit complex. And when there's this subscript x appearing, what I mean is that I'm turning that thing into a certain D module. So this D module has fibers that have to do with tensor products of the graded pieces of this Lie algebra homology, this Lie algebra homology complex. Yeah, so this tensor product, it's a kind of locality also. It's a kind of factorization. I just want to point that feature out.
So is it graded?
This complex? No, but it lives on the space of divisors of total degree lambda check. And as such, it encodes kind of the lambda check. Well, no. You mean, is it an actual complex? Yes. So if you take the C bullet of n-check, it's an actual complex. So it lives in degrees less than or equal to 0, right? The miracle is that this thing, well, we'll comment on it on the next slide, but the miracle is that this thing actually lives in cohomological degrees 0 on these symmetric powers of the curve, but they're not Lie's sheaves or whatever. So when you take the fibers at these diagonal points, they really go down to degrees less than or equal to 0. So there's no contradiction in mathematics that these are concentrated in degree 0, although the homological Chevalley complex itself is not. It's great. OK, and then there's just a comment on homological shifts to make sure this thing is actually in degree 0 as opposed to any other degree. OK, so it's maybe not 100% obvious that this implies the more concrete result I said before, but don't worry about it. It's not hard to see, and it's not worth talking about either. OK, so this D module, it has a factorization structure, which I pointed out already. That's the fact that its fibers are described in terms of tensor products. And in a certain technical sense, this encodes the co-commutative coalgebra structure on the homological Chevalley complex. And you can, like, if you don't like those words, then you don't really need to know what they mean. But I want to point out one of the salient features about it. So what Kozel duality says is that this Lie algebra homology, it remembers everything about representations of this group n-check. And this group n-check, it's the most complicated part in the Langlands dual group, like if you think about Serre relations or whatever. So this is a kind, it's like honest Langlands duality. You're really recovering the group n-check, and it's really the Langlands dual group. It's not just numerics like the first result was. Or who cares if it's, in terms of weights or co-weights. OK, so a couple comments about this theorem. So first of all, geometric Langlands, it usually passes through the geometric Sitaki theorem first. Like that's how you just connect in any way the group and the dual group. So there is this geometric Sitaki theorem. It says something, and well, this result, it's actually different. Like so to speak, the fibers aren't like, well, it compares to this result on intersection cohomology of Drinfeld compactifications I talked about before. There you see Langlands dual group appearing in some vector spaces, but those vector spaces come as cohomologies of sheaves that come from geometric Sitaki. This is like, it's really not occurring in that way here. Probably. So it's related to the paper where they talk about the cohomology of the small quantum group. So this FFKM paper, so it's very similar to this idea. So I'm just too ignorant to say further. And it also follows this Braverman-Gatescory paper that I cited earlier. So I'm not saying that this is like. So the way that this result works, I claim, is that, so this Braverman-Gatescory paper was following the Fagan, Finkelberg, Kuznetsov, Mirkovich paper. And essentially the second result, the kind of interesting one about the Chevalley complex, follows by combining results of Braverman-Gatescory with this vanishing theorem for the intersection cohomology sheaf. So moreover, this observation that this thing is actually in the heart of the T structure, that it's a D module, this was already observed by Braverman and Gatesgory, but it's quite a miracle. So this was the thing I explained to Misha before. There's no contradiction. The star fibers a priori only live in degrees less than or equal to 0. The homological Chevrolet complex does too. So, OK, and moreover, this as a sheaf, so I said it lives in degree 0. It's a perverse sheaf, and you can describe it completely in terms of like the basic operations of perverse sheaves, like middle extension and star extension. From like the generic locus, for example, well, you move over various divisors in terms of the combinatorics of G check. So this is, in a way, it encodes the combinatorics of this Langlands dual group in a geometric way. So you can say that this is like it's a geometric version of the Cartan matrix. And this is ultimately how you prove this result. So since you don't have, since I'm saying this is different from geometric Sitaki, you need to find some way to pass across the combinatorics, and this gadget does it for you. OK, so now I just want to give a sense for how this result is proved. So first of all, the second result, the one about the Chevrolet complex, it follows from the first result, like I said, using the study of, intersection cohomology of these spaces by Braverman and Gatesgory. So now we just need to see the vanishing of this twisted cohomology. So first of all, as I've said several times, if lambda check is a simple co-root, then this vanishing, it just, we proved it on slide 2 or something like that. It was the the Zastava space is basically just A1 crossed with the curve, and it's the vanishing of twisted cohomology of A1. So now, if you do this factorization, what that tells you is that, OK, you have the space of divisors, everything away from that main diagonal of divisors concentrated at a single point, everything has to do with lower Zastava spaces. So what that means is that this cohomology is just going to vanish away from that locus a priori by induction. Everything is in terms of lower things, so you're fine. And so for example, one thing that tells you is it's now circular, but it reduces to a computation for this Zastava space for just the fiber alone. And now there's a complete, so now I'm hiding everything, so you obtain it from the fact that a lot is known about these Zastava spaces. But the thing I really wanted to point out is that this, so it's not a fiber-wise computation. It's something that you use this vanishing away from this locus. So you use the existence of this big space and the kind of cohomological bounds you get on perverse sheaves for free. Well, not for free, from the BBD theory and everything. So this is the point where something really happens, and it's exactly the point I'm hiding. But it gives a feeling for, at least for how the thing is proved. OK, so now a couple more comments. So this paper I cited earlier on my website, it does establish some kind of compatibility between geometric Sitaki and this construction. So geometric Sitaki realizes the category of representations of the Langlands dual group in terms of, the geometry of the affine Grassmannian. So but you should remember representations of the Langlands dual group. So just the terms, just to give a feeling for what this compatibility is, the terms of this are about the Lie algebra homology of n check with coefficients in a representation of the Langlands dual group. Moreover, there's a compatibility with the fusion structure on, in this geometric Sitaki theory. So this is kind of the most interesting part. So this geometric Sitaki finds the whole symmetric monoidal category on the affine Grassmannian, and the commutativity constraint in the construction is given by some very interesting geometry, this Beilinson-Drinfeld Grassmannian. It's been mentioned several times. And you can do essentially a version of this theorem of this second computation with the Beilinson-Drinfeld Grassmannian to get a much stronger result. But it's to say it sees the tensor product structure also. OK, so now I want to discuss some applications of this result to some infinite dimensional geometry. So first of all, the semi-infinite flag variety is something that Fagan and Frenkel introduced into geometric representation theory. And their idea was that there should be some kind of nice space that parameterizes g of k mod n of k t of o. So it's pretty close to g of k mod b of k, but I extend by a lattice. And you can think of this as a kind of different analog of the flag variety for the loop group. It's just a different one. Unfortunately, the space, it just completely doesn't exist as an object of algebraic geometry. Taking the quotient of an in scheme by an in group scheme doesn't have good properties. So it's not so amenable to usual combinatorics or anything like this. But the good news is that you can still make sense of the category of D modules on the semi-infinite flag variety. So just to give a feeling for how the thing works, so the semi-infinite flag variety, it's some quotient of the loop group. First, we want to define D modules on the loop group. And by the way, you have to do this because on Monday, I told you what D modules on any pre-stack, locally almost a finite type was. And this g of k, it's of infinite type. So it's a real thing. So just to give a feeling for the definition, it's by reduction to the finite type case. So you take a so-called compact open subscheme of this g of k and map it to finite type schemes, and then do pullback, push forward, and that gives a typical object. You're also allowed to take infinite direct sums and cones of such things. So exercise for people learning category theory is to rephrase this in the language of limits and colimits. So now we can take this category of D modules on the semi-infinite flag variety to be, by definition, the co-invariant category for D of g of k. So some kind of, smaller version of the kind of Jacquet module or whatever. So it's some quotient of D of g of k, where we basically say, those D modules, we quotient by those D modules on the loop group that should push forward to 0 on the semi-infinite flag variety. OK, so what I want to talk about now is a Langlands duality theorem for this category of D modules on the semi-infinite flag variety. So the format of local geometric Langlands is as follows. So if you have a DG category acted on by the loop group, so Ben Zvi talked about earlier today what it means for a finite dimensional group to act on a category. And there's a version of this for the loop group just as well, as soon as you've defined everything. And then what you expect is that if you take the so-called Whittaker category, which Dario will talk about in more detail, that this decomposes over the stack of local systems for the Langlands dual group on the punctured disk. So Whittaker means, I told you there's a character of this n minus of k, and you should think, you should think in classical terms, it's just a usual character. I can take vectors in a representation equivariant against a character, and that's what this thing is. And what you expect is that this thing decomposes over the stack of local systems. And roughly what it is if you think C decomposes as a bunch of irreducible representations, then maybe you would get a measure on the space of local systems. And this is something like that measure. OK, so there's this rich body of conjectures in local geometric Langlands. And if you think about it, what you expect is the following. So the category of Whittaker D modules on the semi-infinite flag variety should be the category of ind-coherent sheaves on this fiber product, which is maybe hard to parse. So it's B-check local systems on the punctured disk. So think a vector bundle with flat connection on the punctured disk, maybe a regular connection on the punctured disk with a complete flag. Then at the associated graded level, you've extended that over the whole disk. So you ask that it be trivial, essentially at the associated graded level, but in slightly different terms. OK, so as stated, this conjecture, it actually follows in an indirect way from work of Sergey and Bezrukavnikov. It's one of the fundamental results in the theory of local geometric Langlands. So I want to discuss an alternative approach now based on those earlier computations to a stronger and weaker result. So here's how you connect that conjecture to our earlier computations. So let this functor of semi-infinite restriction be the kind of restriction functor from Ger T to the semi-infinite flag variety. So this functor, I said the space doesn't make sense, but this functor does between the category of D modules. And what this does is it takes D modules on the semi-infinite flag variety and produces lambda check graded vector spaces out of them. So now, just some words to keep in your head. So maybe it's, OK, I'll recall the construction when I need it. But for people who can keep these things in your head, I'm going to define two things called the unit object. So the first is the Whittaker sheaf on the Grassmannian, which is like you take this n minus of k orbit, you take it, like since residues vanish on n of O, there's some Whittaker sheaf on there, and you just extend it. It doesn't, turns out the Schrick and star extensions are the same. So this is the so-called unit object. And we get a unit Whittaker object on the semi-infinite flag variety in a standard way. So you pull back and push forward along the only thing you can. And again, it makes sense by just the construction of D modules on the semi-infinite flag variety. So just remember that there are these unit objects. So first of all, I claim that computing the semi-infinite restriction of this unit object, it's the same as the computation we did before. So here we're in this like wild world of infinite dimensional geometry. But actually, I claim that this comes down to computing these concrete invariants that we had before. So namely, OK, I said what this unit object is. So you start in the bottom left corner with the Whittaker sheaf on ger n minus. You extend to ger g. You pull back to g of k mod b of O. You push forward to the semi-infinite flag variety. And then you pull back to the affine Grassmannian for t. So you go down the lower leg and then up to the top. So now, of course, we're going to compute this by base change. So you form the fiber product on the right. And what you end up with is ger b, the affine Grassmannian for b. And so you should push forward, pull back, push forward. But well, now we're pushing forward, pulling back twice. So that means I just need to push forward to ger g. OK, I should form the fiber product on the left, is what I'm trying to say. You should push forward to ger g, pull back to ger b. And by definition, what that fiber product is the disjoint union of these Zastava spaces. It's the intersection of these locally closed things inside of the affine Grassmannian. OK, so now I want to connect those computations with these earlier conjectures, this Langlands duality for D modules on the semi-infinite flag variety. And so in order to do that, I'm going to need to appeal to the so-called factorization structure on the semi-infinite flag variety. So I'm using factorization in the same sense, more or less, as I used it for Zastava spaces before. So roughly, here's what it is if you've never seen this stuff before. So if you have a point in your curve, you can think there's a semi-infinite flag variety at that point. So you just take Laurent series and Taylor series based at that point in your curve. And then well, if you know the Beilinson-Drinfeld-Grassmannian or whatever, this shouldn't be surprising to you that there's a version that depends, so to speak, continuously on a finite subset of the curve. And its fiber at those points is this product of semi-infinite flag varieties. But as the points collide, different factors eat each other up. So then this computation I did of where the unit object goes, it works just as well in this setting. And essentially for the reason that we did our computation for Zastava spaces factorizably. So that gives us enough control on this factorizable computation. OK, so now I want to construct a functor that has to do with this Langlands duality conjecture from before. So I'm going to do it using a toy model. So here's the toy model. So suppose that you have a so-called lax monoidal functor between monoidal categories. So lax monoidal functor, it's a technical categorical term. And roughly what it means is that every time you have a pair of objects f and g, well, normally for monoidal functor, you ask that f of f, tensor f of g, be isomorphic to f of f, tensor g. Here, you only ask that you have a map like this. So the basic example you should keep in mind is that f is the restriction functor for a map of commutative algebras. So if you tensor over A, then that maps to the tensor product over B, if you start with two B modules. So in this case, this functor f, which maybe forgot a lot of information, like it might be this restriction functor from B modules to A modules, it automatically upgrades to a functor that remembers more data. So it now goes from this category C to the category of modules over the image of the unit object in C. So for example, in this case, when f was the restriction functor from B modules to A modules, this enhanced functor will now go from B modules to B modules. So it's something that remembers more information. And of course, if you compose this f enhanced with the forgetful functor to D, then you recover f. So now I want to appeal to this in this factorization setting. So the point is that just like on the last slide, there's a kind of abstract algebra formalism for these factorizable geometry. So this is, it was introduced and developed by Beilinson and Drinfeld in their book Chiral Algebras. And then I have some notes called chiral categories on my webpage that are designed to do exactly the construction I'm talking about now. So first of all, in this language of abstract algebra, you should think about this semi-infinite unit object as, well, the unit object, like that object 1 from before, in the Whittaker category. So now what this formalism tells you, just like the toy model, is that you're going to get a functor of factorization categories that now goes from Whittaker modules on, OK, so we had the Schriek functor, right, the Schriek restriction, that went from D modules on the semi-infinite flag variety to D modules on the Grassmannian for T. So lambda check graded vector spaces, but factorizably. And now what I'm telling you is that if you take Whittaker objects, then you know where the unit goes. It goes to this nice Chevrolet complex for the Langlands dual group by our computations earlier. So that's where Langlands duality is occurring. And now we get this enhanced functor that goes from the category on the left to modules over the image of the unit, where we've computed the image of the unit using these finite dimensional calculations, and so coming fundamentally from these Zastava space calculations. So we get this nicer functor. It automatically goes to so-called factorization modules for this factorization algebra. But it's great. Now everything over, this is Langlands duality. The left-hand side is in terms of the group G. The right-hand side is in terms of the group G check, up to replacing T by T check. I mean. Exactly. Yeah, that's where it comes from. So. OK, so now I want to talk, obviously, about this functor, this enhanced restriction functor. So first of all, OK, just purely on the Langlands dual side for this slide. So I want to say what this has to do with our earlier conjecture. So specifically, if you take IndCo of that fiber product I talked about before, it maps to this category of factorization modules. So again, everything is on the Langlands dual side. And what I want to say is that the right-hand side, it's a really good approximation to the left-hand side. So you have a functor, and it's very close to being an equivalence. It's close in the sense that there's a full subcategory of the left-hand side that actually maps isomorphically. So this is a kind of Verdier quotient operation from the left-hand side to the right-hand side. And yeah, and just for people who can keep this stuff in their heads, really what the category on the right is the category of sheaves on here supported on the diagonally embedded copy of B-check local systems on the disk, like on the non-punctured disk. So this right-hand side is suddenly a good approximation to the left-hand side in this precise sense. And as I said, the left-hand side is what occurred for us with these Whittaker sheaves. Well, it was our conjecture about what Whittaker sheaves on the semi-infinite flag variety should be equivalent to. So theorem that should be available soon is that this functor, it's as close to being an equivalence as possible. Namely, there's a full subcategory of this category of Whittaker sheaves on semi-infinite flags for which, the induced, if you restrict to that subcategory, you get an equivalence. So there's a certain explicit full subcategory. So this is compatible with the Arkhipov-Bezrukavnikov result, though their construction is just completely different. So yeah, so it's a strengthening in the sense that it involves this factorization structure, and it's a weakening in the sense that I'm dealing with some full subcategory, though maybe in time that'll be corrected. And yeah, so I just want to say that the terms in which Arkhipov and Bezrukavnikov work, they're just, well, I said that the comparison is roundabout. And when you do this roundabout comparison, you just totally lose all factorization structure. So it's really of different nature. So now just some quick discussion of applications of this result. So the first thing is that you can obtain some kind of factorizable decomposition of this maybe version of category O, if you like, of n of k equivariant D modules on the affine Grassmannian for G. So it's whatever this theorem says, it's in very similar terms to this conjecture I stated for Whittaker D modules on semi-infinite flags. So it's some local systems on the punctured disk, blah, blah, blah. Though G-check itself appears in this case. And this result recovers a later result of Arkhipov, Bezrukavnikov, and Ginsburg in a roundabout way if you fix your point. So moreover, you can use this. And by the way, here you obtain the full category, just unconditionally. So now, moreover, you can use this equivalence to compute, well, David Ben-Zvi told us today something about, gave us some feeling for what chiral homology is, and whatever it is, you can use this equivalence specifically in its factorizable form to compute these chiral homology groups. With these, well, so chiral homology is some way of passing from this factorization stuff to global invariants. Finally, you can use those computations to settle some of the outstanding issues in Dennis's project around the geometric Langlands program, and specifically around the Eisenstein series part of it. So namely, well, I said on the last slide that there was this GERG n of k. So remember that Dennis stated on Monday an equivalence between a category he called I of GB, which was something like D modules on the following space. So G of A mod G of O mod n of A, and then you throw in T of the rational functions valued in T on your curve. And so if you ignore that B term on the left, then this is essentially G of, it's a kind of restricted direct product of the Grassmannian mod n of k. So no surprise, maybe, that this has to do with that local description, the local spectral description. And it's equivalent to something in terms of the Langlands dual group, which you can think of as quasi-coherent sheaves on, oops, that's a typo, locus, oh, two typos, locus B check of the curve x with connection along the fibers to the map to G check local systems on x. And this, OK, now it's correct, is what Dennis called today in his talk, indco sub 0 of this fiber product. So it's the category which is occurring in Dennis's talk. He said on Monday he gave this motivational talk about relating some principal series categories on Langlands dual sides, and in order to give this gluing category for Langlands duality, for global Langlands duality, and this is where that stratum-wise equivalence comes from. So it's ultimately from these local computations, and ultimately from these computations of twisted cohomology on Zastava spaces. So thank you so much for inviting me to talk.